Okay, welcome everybody to another empirical economics lecture. Before we begin, let me just announce that we had a little survey last week after the study break whether or not you liked that, and a large majority of you seemed to like the study break, and because of that we have another break today, now at roughly 1 o'clock, so somewhere between 12:55 and 1:05. And we'll just build that into our lecture at a point that suits us well. Now let's get started. Let me just share my screen. There we go. We summed up last week with the fact that we still want to know what the relationship between class size and the outcome of the students is, the learning outcome of students is. But we found that there are some difficulties, for example, that the treatment, in this case class size, is not randomly assigned between students, but we have observational data and not experimental data. So some districts have smaller classes, some districts have, of course, larger classes, but students are not randomly assigned to larger or smaller classes. So maybe our first OLS assumption might be violated. Today we are going to address precisely this topic, namely, we are starting with omitted variable bias, and then we come to how, at least to one way of how we might solve that bias here. So remember, our simple linear regression model yielded that we have a relationship between test score and student-teacher ratio that says that for each student we put more into a class, the average test score is expected to decrease by 2.28 points. So the question here is now, obviously, now we've seen that result, is that a good estimator for the causal effect of a change in class size on our test score? Is that a reliable estimator? And the answer here is unfortunately no, it's not. It's not at all, because we have many factors. For example, the family income around a district, or very much related to that, the possibilities of children to learn outside of school, to get support by their parents, and so on. So many effects that are, on the one hand, related to student-teacher ratio, and on the other hand, have an influence on the test score. And that problem is called omitted variable bias. And as you can see here in this definition, an omitted variable bias, or an omitted variable that, so some variable that is outside of our regression, because just recall we only included variables x and y up to now. That variable causes omitted variable bias if the variable z has an effect on the endogenous variable y. So the income of the parents probably does have an effect on the learning outcome of the students. And secondly, and also very important, is correlated with our exogenous variable x. So if the income of parents is correlated with the class size, so wealthier districts have smaller classes, and at the same time wealthier districts have better test score, then we have an omitted variable bias, because we neglected that wealth or income of parents has an influence. So if both of these conditions are met, and you will generally very often find variables that are omitted from regressions that are in fact correlated with the exogenous variable and have an effect on the endogenous variable, then you have omitted variable bias. And then our coefficient beta 1, so our estimated causal effect, deviates significantly from the true value, even if the sample size is large. So it doesn't help if we take more and more school districts around the world, around the United States, and take more and more data. It won't help. Some problems you can sort out by just getting larger and larger samples. Omitted variable bias is not one of them. So our estimator here is systematically wrong, and everything we get from such a regression is in itself significantly and substantially wrong, and we cannot and must not rely any interpretation on such a biased output. Let me just give you, first of all, a way or a diagram that shows you how the mechanism works, and then after that, a little example. The example here is that we have, or it's just a diagram of the very same story I just told you, or that you could see in the definition. We have a variable z, and the variable z has an influence on both, on our regressor of interest and on our endogenous variable. But if we exclude that variable, if we only look at the relationship between x and y, we would exclude substantial other relationships from our regression, and thus our regression will suffer from omitted variable bias. Let's have a look at an example. If you want to consider factors that influence the vocabulary of children, then you could also, of course, measure the weight of children, and you can measure the vocabulary based on the number of words the child uses per average per day or something like that. And then you would definitely observe a very interesting and very puzzling relationship, namely that with increased weight, vocabulary increases as well for children. So feeding them a very nutritious meals might be a very good idea to increase their vocabulary, and with that, of course, increase later on their school outcomes and maybe their income in later life. Obviously, that doesn't seem very logical, and that doesn't make any sense at all, because what you would omit in this case is the variable that drives both of these variables, that drives weight and that drives the vocabulary of the child, namely the age of the child. Older children obviously weigh more than younger children, and older children obviously had a longer time span to learn new words, will have acquired a larger vocabulary, and hence age here is the main driver of vocabulary. If you run a regression that includes weight and age, then weight should not be might not be a significant factor for vocabulary at all. Which brings us to our example here. We have our student-teacher ratio and test scores. Obviously, student-teacher, or not obviously, but we suspect that student-teacher ratio has an effect on test score. We would also suspect that the share of non-native speakers in the class, so this is written down here with PCTEL, is the percentage of English learners in a district, so the persons that are non-native speakers, that this fraction of the total students also has an effect on test score, because test score is combined of the math score and the reading score, and at least the reading score should be in some way affected by whether or not the person is a native speaker or not. But if now student-teacher ratio was correlated with the share of non-native speakers in a district, so for example, districts with a large share of non-native speakers would have larger classes on average, then we would observe a distortion of our coefficient of student-teacher ratio on test score. And that's, at least for one example, what is exactly happening in our data set. Now let's have a look at STR and test scores in the California dataset. So do our two conditions hold? Do we see an influence of PCTEL on test score, and do we see a correlation between these two, between student-teacher ratio and English learners percentage? So the first one, we can only say that, yeah, probably there is a relationship between the fraction of persons learning English and the test results. Secondly, our second condition that needs to hold for us to have omitted variable bias, it's also very likely because districts with many immigrants tend to be poorer in the US, and because they are poorer, schools can't spend that much money, so on a tendency they have larger classes, so our variable Z the English learners percentage and our variable x are correlated. So our estimator is biased. The question that arises now is, in which direction might that estimator be biased? So is our estimator, you remember we had it roughly minus 2.3, is that estimator too large? And too large here means an absolute value. So is the correct value maybe minus 1 or only minus 0.5? Or is that estimator too small and actually the effect is much stronger than the one we estimated? And to that end, it helps to look at a little formula, at the formula for our bias. The left-hand side, so this one is something that we've already seen, that our estimator converges in probability to our true value, to our true coefficient, to our true relationship between, in this case, test score and student-teacher ratio. On the right-hand side, what we are adding here is the variance or the standard deviation of our error term divided by the standard deviation of our regressor. So a fraction of how much more does the error term vary compared to the regression, to our regressor. But most importantly, we also we multiply this with the correlation between our regressor and our error term, something we would not, we assumed to be 0 in our first assumption. But in this case, in fact, this correlation is not 0 because we have a direct relationship between the deviation from our regression line and our student-teacher ratio. So if this correlation coefficient is positive, then the effect that we estimate is larger than the actual effect. And if the correlation is negative, then the effect we measure is smaller than the actual effect or the true effect is. And only if this correlation is 0, so the thing we assumed in the first assumption, then we have no omitted variable bias. So take that in mind, that it's very important that the first assumption holds, and that whenever the first assumption is violated, we would obtain a bias estimator here, and we could not at all solve that by just taking more and more people into our data sets or by increasing our data sets. Okay, let's go over to Mr. Trede, who is giving you an example of how exactly omitted variable bias works in our example.
Right, thank you, Andreas. Just share my screen. So the question now is, what is actually the effect of this omitted variable bias, of this confounding effect on the sign of the bias we have? So as we have just seen in the formula for the bias, it all boils down to the sign of the correlation between the regressor, in this case the class size, and the error term. And that's because on the previous slide, these two terms must be positive. So the standard deviation of the error term cannot be negative, and the standard deviation of the regressor cannot be negative either. So both these terms are positive, and the sign of the bias is the deviation between what we estimate for large samples and the true value. So the sign of the bias, of this bias, must depend on the sign of the correlation coefficient. So the question is, what is the sign in our particular running example, say in the test score, California test score data set? And to think about that, we start by looking at some district where the variable PCTEL, so the percentage of English learners, is large. So think about a district where we have relatively few native tongue students. So English is a foreign language for many students in that district. So it's likely that this district has a large number of immigrants, which means that for those children, it's much more difficult to actually do well in the tests. and therefore the error term tends to be negative. So there's a direct effect of the percentage of English learners on the error terms, and this effect will be negative. So the larger the share of English learners, the worse the error term, or the more negative the error term will tend to be in those districts. So we have a direct effect of the confounding factor, the omitted variable, which corresponds to the Z variable in the previous abstract example, on the error term. And second, if we look at a district where the percentage of English learners is large, so where many immigrants tend to live, then those districts are those that tend to be relatively poor in comparison to other districts. So it's a poor district, and that means that this district has fewer tax revenues and therefore less money to spend on schools. And therefore, these districts will have, on average, larger classes. So the regressor in our case tend to be large. So there's a correlation between the confounding factor and the regressor. So both conditions are met. We have a relationship, a direct relationship between the confounding factor PCTEL and the error term, and we have a correlation between the omitted variable and the class size. And therefore, if PCTEL is large, then the U tends to be negative and the classes tend to be large, so positive. And therefore, there's a negative relationship between the error term and the regressor. Okay, so if we look at districts where PCTEL is large, then we have a small error term and large classes, not always, but on average. And if PCTEL is small, so most students speak English well, then the UIT tends to be positive and the class sizes tend to be small. So positive error term and small class sizes, and we have a negative relationship between these two variables, and therefore the correlation coefficient is negative, which means that the value that we estimate from our data, at least in the long run or for large samples, is not only the true value, but we have to add something, and what we add is negative. So we actually subtract something, and the estimated effect is smaller than the true effect. Okay, and since beta is negative, that means that it's larger in absolute value. And I think it's a good idea to illustrate that with a little graph, and I will do so. I will try to do so now. So let's try to share my writing pad. All right. So let's look at a simple example. We have our coordinate system. We have the test score as our dependent variable. And we have the class size as our regressor. Then suppose there's some true relationship between these two. Let's assume it's negative. And then we look at the data points. Suppose we have a large class size. So we are in this area around here. And let's assume that this class size is large because the district is relatively poor and tends to have a relatively large number of immigrants. So it's a poor district, and therefore the test score tends to be worse than the regression line actually would tell us. And therefore in this area, where the class size is large, the residuals, the error terms tend to be negative. Sometimes it might be positive, but on average it tends to be negative. While if we look at small classes down here, then the error term tends to be positive. Not always, but on average. and in between, it's just scattering around. Okay. So now if you squint your eyes, then you will realize that if you put a regression line through the dots, then what you get is something like this, which is obviously not the true regression line. Okay. So the red line is the one that we estimate from our data points, while what we are interested in from a policy point of view would be the blue line, not the red one. And that's a problem, because if we use the red line to do policy recommendations, then we would tell the policymakers that decreasing the class size, say from here down to here, would increase the test score by quite a bit. Well, not overwhelmingly much, but at least a bit, because that would be the increase in the red line. So it would increase a bit. But in fact, the effect is much smaller. It's only the one that's given by the blue line. So we think that our empirical investigation tells us that decreasing the class size has an effect which is shown by the red line, so relatively large, but in reality, the effect of decreasing the class size is much smaller. It's only given by the blue line. And the reason for this discrepancy between these two, the reason for this so-called omitted variable bias, is that one important variable, the percentage of English learners, is missing from our picture. So it does make sense to look at the red regression line if you are interested in estimating what the test score, the average test score, would be in a class of a given size. But that's something different from a causal interpretation. A causal interpretation would tell us that increasing or decreasing the class size in a certain situation, holding all other variables constant, would have a certain effect on the test score. So certain policy success, if you like. And this policy success would be estimated by the red line. That's wrong. The true policy success would be given by the blue line. And you can even imagine a case where the blue line is upward sloping, but the red line is downward sloping. It all depends on the size of the standard errors of the regressor, the error terms, and the coefficient between these two variables. Okay, so that's really a severe problem. And we must be very careful when we would like to interpret the outcome of a linear regression in a causal sense, because very often this causal interpretation is just not valid. Any questions so far? Okay, so let's come back to the main slides. All right, so we have seen that the causal interpretation is really a problem. And now we look at the data more deeply. So let's look at this table and let's look at the red part first. So here, the entire universe of school districts in California is subdivided into two parts. First, we have the group of small classes, smaller than 20. And then we have the group of large classes, here defined as 20 or more students per class on average. Then we have the average test score for the small classes, 657. And we have the average test score for the large classes, 650. Actually, we did this last week when Andreas showed you how to do linear regressions with a dummy variable. And he introduced a dummy variable for small classes and large classes. And these were the outcomes that we could see in that example. So it's exactly the same as last week. So the difference between these two is 7.4 points. So large classes do worse than small classes. And last week, we also have seen that the t-statistic for this difference is roughly 4, which is larger than the typical critical value, 1.96, and even larger than the critical value at the 1% level, which is 2.3 something or so. So it's significantly larger. Well, smaller. In the large classes, the learning outcome is significantly worse than in the small classes. All right, that's the overall picture. But now let's look at the confounding factor, the percentage of English learners, at the omitted variable. And let's subdivide each of these two groups, the group of small classes and the group of large classes, according to the percentage of English learners. So let's start with those districts which have a very small percentage of English learners. So these are the districts where most students can speak English as a native tongue. So they will understand everything the teachers tell them because there's no language difficulty for them. And now let's look at the test scores, the average test scores for those districts where only few students have a foreign language. And again, look at small classes and large classes in that case. And we can see that the small classes for those districts where the percentage of English learners is very small have an average test score of 664.5, while those which are large, the large classes, have an average test score of 665.4. So actually the large classes do very slightly better, not worse, but better, even though they are larger, than the small classes. So the difference is minus 0.9. If we compute the t-statistic, it's minus 0.3. That's not significant for any usual significance level. So the difference between small classes and large classes is not significant if we only look at districts with very few foreign language students. Right, let's continue with the next group. So this is the modest amount of English learners. And again, we can see that the difference between the small classes and the large classes is not very large. In this case, the difference is just 3.3. The large classes do slightly worse than the small classes, but the difference is not very large. And again, if we look at the t-statistic, it's not significant for any usual significance level. And if we continue with a relatively large amount of English learners, then we can see that, again, the large classes do a bit worse, and the difference is a bit larger. Now it's 5.2, but again, it's not significant at usual significance levels. And if we only look at those districts where the number of English learners is the percentage of English learners is very large, more than a quarter almost, then we can see that the difference between small classes and large classes, again, almost vanishes. So it's 636 against 634. So only roughly 2 points difference between small and large classes if we only focus on those districts where many students are foreign language students. And again, it's not significant. If you look in this direction, then you can see that those districts with few English learners have relatively good scores, 664, 665, but then it decreases. And districts with many foreign students obviously have more difficulties to get good test results. And the same is true for the large classes. So there's a strong effect of the percentage of English learners on the learning outcome, but within each group, there's only a small and insignificant effect on the learning outcome of class size. All right, so we can see here that obviously the percentage of English learners has a strong effect on the learning outcome, while the class size for each of those groups only has a very small and insignificant effect on the learning outcome. And only if we aggregate over these four groups, and then we would end up in this top line again, only then the difference is large. So please notice that this difference, 7.4, is actually larger than any of these differences here. And it's significant while each of the subgroups is insignificant. Okay. All right, so if we look at the data in this way, then we can see that districts with low percentages of English learners, so with many native speakers who speak English as a native tongue, have better test scores. We can also see that districts with low percentage English learners have small, we know, we can't see that in that table, but we know that on average districts with low percentage of English learners have smaller classes, because those tend to be the richer districts who have more tax revenues, and therefore are able to afford smaller classes because they can hire more teachers. There's only little impact on the class size on the test scores for districts with a similar percentage of English learners. So within each of these strata, there's only a small effect of class size. And we can even see that in each group, the impact of the class size is smaller than in the total population. All right, this is a look at the data. So let me return to Andreas again. Andreas, du hast das Mikro noch aus.
Thanks, welcome back from my side. We have now encountered another very influential factor on learning outcome. So the number or the share of English learners in a class, in a district. The question is now, how can we incorporate that additional factor into our model? Because our model up to now was only able to incorporate a single variable, and we used that to plug in the student-teacher ratio as variable. Luckily, it's very simple to do so by just adding these different other variables we might be interested in into our model and end up with a linear regression model, but now not with a single regressor, but with multiple regressors, and we call that the multiple linear regression model. And in our case, in the notation here, we have small k exogenous variables, so small k regressors. So what we do is the left part that I'm just marking with my cursor is something we already know. That's what we've already seen. But if we want to add more regressors, we are free to do so by just adding them. And all of these additional regressors, of course, have their coefficient that shows us the influence of these regressors. In fact, beta 1 now, our coefficient of interest, our coefficient that measures what's the effect of student-teacher ratio, is now the change of y, or the effect of a change in x1 on y, if we keep all the other regressors. So if we keep the English learners percentage or the family income, or so all the other regressors, if we keep them constant, then beta 1 measures the effect of a change in student-teacher ratio. So for example, increasing class size by 1 pupil on learning outcome. X2 then on the other hand is of course the effect of changing the English learners percentage by 1 percentage point on learning outcome. Now, student-teacher ratio obviously might have a causal effect. Whether or not other variables have really causal effects will be up for discussion. We will see that in later slides. And UI, again, as before, is our error term. So back here. Now, how can we interpret our coefficients? As I just said, it's the change of y if we change x by 1 unit. So let's have a look at that mathematically. So we change x1 in our model by delta x1. So we increase our class size by, for example, 2 students. We keep x2 constant. So the percentage share of English learners in that district stays constant, needs to stay constant. So in our real example, that would mean that we, of course, needed to include students that reflect the English learners percentage in the district to our class. So we won't change that if we really did that in an actual application. But this is just a thought experiment. Now, our population regression, now it's obviously a surface, no longer just a line, because we're going into 2 dimensions. We will have the surface here. Let's have a look at that before and after the change. Before the change, it's just y is equal to beta 0 plus beta 1 times our current level of student-teacher ratio, x1, plus beta 2 times our current level of PLECT, or x2. Now we said we increase our first regressor by 1. And let's have a look at what happens on the left-hand side. So on the right-hand side, we increase x1 by delta x1. Sorry. And on the left-hand side, yi changes as well. So yi is added by some delta y. We don't know yet how much that is, and that's what we are going to find out by simply subtracting these 2 surfaces, one from each other. So we take our changed variable, so the equation where we increased x by some unit, by some quantity, and subtract from that the regression surface or regression line that we had without increasing or without changing x. And what happens here is, of course, the beta zeros cancel out. On the right-hand side, beta 2 times x2 also cancels out. And on the left-hand side, y and y cancel out. So what we are left with is the change in y. So by how much does y change is equal to beta 1 times the change in x1. So beta 1 times the change in student-teacher ratio. Now we can divide that by delta x1 to isolate our coefficient, and then we see that the coefficient is nothing else than the slope of that surface in direction of x1. So the change in y, so the change, increase or decrease of our test score divided by the change of our student-teacher ratio, so the increase or decrease of the student-teacher ratio. And that holds true not only for beta 1, but also for beta 2. And obviously, if we have k regressors, that would hold true for beta k and all the regressors up to beta k as well. Now, we've talked about the coefficients beta 1 to beta k. Now, beta 0 is still our constant in the regression. And now it's the forecast for y if all of the regressors are 0. In our running example, that doesn't make sense because that would imply a student-teacher ratio of 0. So 0 students per teacher doesn't make sense. But x2, on the other hand, might be 0. That makes totally sense. If we have no non-native speaker in our class, that value can be put into context. But technically, if we set all the variables equal to 0, then beta 0 gives us the forecast how large would our test score be if I set all my regressors to 0. Our OLS estimators can now be derived in the very same manner, in the very same way as we did that with the simple regression model. The only difference here is that, of course, we do no longer minimize the sum of the squared deviations of yi and b0 plus b1 xi only, but of course we also add all the other regressors because now we have them inside the model. And now our error term is the difference between yi and b0 plus b1 xi plus b1 x2i and so on. So that's basically the only difference we see here compared to our single linear regression model. And again, we can run these minimization routines by standard routines. We don't need to do that ourselves, luckily, but we can let R do that. And R can compute, or any statistical software will compute the results from this minimization routine and give us the multiple linear regression model. It gives us estimates in R for all the coefficients that we want to have estimated. The notation also stays the same. Beta 0 is again, a beta 0 hat is the estimator for our constant. Beta 1 hat to beta k hat are then the estimators of our OLS coefficients. of our regressors. And predictions are then, of course, not computed by only including a single regressor into the model like we had before with a simple linear regression model, but of course, the prediction now for the test score depends on class size and, of course, on the English learners percentage in our school district. So we have to include all the variables that we have in the regression model into our prediction. And last but not least, from a notational side, the residuals are defined just in the way we defined them before, just as the difference between the data we observe, so the observed test scores minus the test scores we would predict with our multiple linear regression model. Let's have a short look at what is going to happen exactly in our school example. Remember our simple linear regression model, where we have seen that test score, that student-teacher ratio influences test score by a coefficient of -2.3. Now, what we do now is we add another regressor. We add percentage English learners to the model. And what we obtain then is a lot different from what we've seen before. Let's have a look at the intercept. That's 686 now instead of roughly 700. We don't want to interpret that that much because it would mean we would need to set str equal to 0. That doesn't make any sense. So let's not dive too deep into the intercept here. We have a coefficient of -0.64 for the percentage of English learners. So the more persons are still learning English, are non-native speakers who might struggle understanding language, and with language, of course, the message of the teacher. So if we have more foreign language students in our class, then on average test scores decrease. But what's most striking is that the coefficient of student-teacher ratio, the coefficient of class size, is less than half as large as it was before. Now the influence of reducing the class by one student is only -1.1 test score points. So we have a much smaller influence now, and that's obviously because test score and the percentage of English learners were correlated. And on the other hand, as we can see here, we have an influence, or we observe an influence of English learners percentage on test score. So we had a very strong and very significant omitted variable bias in that very first regression. We still can't say that we do not have any omitted variable bias down here, because we still have many variables unaccounted for in this regression, but we can see already that the influence of student-teacher ratio, the influence of class size, seems to be much weaker than we had firstly anticipated and firstly seen in our simple regression model. I think it's now a good time to introduce our active break for today. So just stand up from your computers, make yourselves comfortable, and I'm going to start the video that the Hochschulsport supplies on their website for you, and we can have an active break together. It takes roughly 11 to 12 minutes, and after that, we are coming back to our regression models. So see you in a bit.
Hi, ich bin Luis, Übungsleiter beim Hochschulsport, und ich heiße euch herzlich willkommen zum Study Break. Am besten habt ihr rechts und links ein bisschen Platz und achtet darauf, dass ihr ein bisschen lockere Kleidung anhabt. Und dann würde ich sagen, fangen wir direkt an. Wir fangen erstmal an, leicht auf der Stelle zu tippeln. Erstmal schön langsam. Erhöhen das Tempo ein bisschen, nehmen die Arme schön mit, achtet auf eine gleichmäßige Atmung. schneller. Und jetzt machen wir einmal volles Tempo. Sehr gut. Einmal schön die Beine auslockern. Kommen zur ersten Kräftigungsübung. Wir ziehen jetzt immer ein Knie auf Hüfthöhe an. Ich zeige euch das von der Seite. Fangen mit dem rechten Knie an und bleiben auch erstmal beim rechten Knie. Schön langsam. Dann machen wir noch 5 Wiederholungen. Und die letzte. Das gleiche machen wir jetzt mit dem linken Bein. Linke Hand ausstrecken und das Knie hochführen. Und 5, 4, 3, 2 und die letzte. Jetzt erweitern wir die Übung ein bisschen. Jetzt machen wir nicht nur die Knie hoch, sondern wir führen unsere Knie zu den Ellenbogen. Das machen wir jetzt immer abwechselnd. Erst rechts, dann links. Das machen wir erst langsam. Erhöhen jetzt das Tempo ein bisschen. Noch ein bisschen das Tempo erhöhen. Noch 5 Sekunden. 4, 3, 2, 1. Sehr gut. Einmal die Hüfte ein bisschen auslockern. Kommen zur nächsten Übung. Jetzt kümmern wir uns um unsere Waden. Ich zeige euch das von der Seite. Wir gehen jetzt immer auf die Zehenspitzen, halten 2 Sekunden oben und gehen wieder runter. Hände könnt ihr in die Hüfte tun. Und 3 Wiederholungen. Die letzte. Sehr gut. Einmal ein bisschen lockern. Die Übung wiederholen wir jetzt gleich noch einmal. Wieder Hände in die Hüfte, Zehenspitzen, halten und runter. Noch 3 Wiederholungen. Hoch, halten und runter. Sehr gut. Als nächstes machen wir ein paar Squats bzw. Kniebeugen. Das heißt, achtet darauf, dass eure Knie nicht über die Fußspitzen rausgehen. Bauch einziehen, Brust raus und Arme nach vorne. Und dann gehen wir runter. Schön gleichmäßig weiterarbeiten, gleichmäßig weiteratmen. Dann machen wir noch 5. Und bei der letzten Wiederholung halten wir ein paar Sekunden unten. Und jetzt halten wir unten. 5, 4, 3, 2, 1. Sehr gut. Als nächstes kümmern wir uns um die Lockerung unserer Schultern. Das heißt, wir packen unsere Hände auf die Schultern und lassen unsere Ellenbogen erstmal nach vorne kreisen. Schön langsam. Das gleiche machen wir jetzt rückwärts. Sehr gut. Einmal die Arme auslockern. Bei der nächsten Übung trainieren wir unseren Nacken. Das heißt, packen unsere beiden Hände verschränkt hinter den Kopf, drücken die Hände nach vorne und den Kopf nach hinten, sodass eine Spannung im Nacken entsteht. Das hängt jetzt von der Seite. Kopf nach hinten drücken, Hände nach vorne. Dann entsteht automatisch eine Spannung im Nacken. Halten die kurze Position. Und locker. Das gleiche machen wir jetzt von vorne. Das heißt, wir nehmen die flache Hand, drücken die vor unsere Stirn, unser Kopf drückt nach vorne, die Hand nach hinten und dann entsteht die Einstellung. Kurz halten. Und locker. Das gleiche machen wir jetzt noch von rechts und von links. Das heißt, wir packen unsere Hand an die rechte Seite, drücken den Kopf nach rechts und die Hand nach links. Das halten wir auch kurz. Und das gleiche jetzt noch von der linken Seite. Kopf drückt nach links, die Hand nach rechts. Und sehr gut. Die nächste Übung ist auch noch für den Nacken. Das heißt, wir gehen leicht in die Hocke, schulterbreiter Stand, Brust raus, machen unsere Hände zu Fäusten und heben die Hände immer wieder auf Schulterhöhe. Wer mag, kann gerne 2 Wasserflaschen in die Hand nehmen. Und noch 5 Wiederholungen. Und jetzt. Sehr gut. So, jetzt müssen wir auch kurz gucken. Als nächstes dehnen wir unsere Wade. Das heißt, der rechte Fuß geht nach vorne, Zehenspitze zieht zum Körper. Und jetzt können wir mit unserem Oberkörper bestimmen, wie stark die Dehnung sein soll. Und lockern. Das gleiche machen wir mit der linken Wade. Geht nach vorne, auf die Hacke stellen, Fußspitze zieht zum Körper und mit dem Oberkörper bestimmen wir die Spannung. Gut zu halten noch kurz. Und lockern. Zum Schluss dehnen wir noch, beziehungsweise lockern wir unseren Nacken noch ein bisschen. Das heißt, wir packen unseren Kopf auf die rechte Seite und lassen unser Kinn über die Brust immer wieder zur anderen Seite wandern. Sehr gut. Das war's auch schon für heute. Ich hoffe, ihr hattet Spaß und dann sehen wir uns nächste Woche wieder. Ciao.
All right, welcome back. Yeah, thanks to the HSB. I hope you enjoyed that break. I, for myself, certainly did. I think it's good to be a little active even in the lectures. So I think let's come back to you, Mark, with some more slides on the topic.
Yes, thanks for organizing the active break. Right, the next topic is actually the same as the one we did last time when we talked about the linear regression model with only a single regressor. So what is actually a way, or what are ways to measure the goodness of fit? How well does the regression actually explain the endogenous variable, the variation of the endogenous variable? That's the question again. So instead of asking what's the measure of fit of a regression of y on a single x, we now ask ourselves, what is the goodness of fit, or how good is the fit of a regression of y on a number of regressors, say k? Can those regressors actually explain a large share of the variation in y, or do they only explain a very small variation of the small share of the variation of y? And in that case, that means that much of the variation in y remains unexplained. It's just hidden in the error term. So in other words, we would like to measure in a certain way how close are the actually observed points, the actual observations, how close are they to the regression surface. So the regression surface, that's the multidimensional equivalent to the regression line in case of a single regressor. And the answer to this question, how good is the fit, can actually be given in two standard ways. One of which is exactly as before, the standard error of regression. So we will reintroduce that again. The second is also the same as before, R squared. And then the second way to measure the goodness of fit will be slightly adjusted, and that's called the adjusted R squared, but it's nothing really new. So let's start with the standard error of regression. Actually, the term standard error of regression is not always used by all computing packages and all textbooks, so there's some variation in the terminology here, but we just stick to the terminology which is used in the textbook by Stock and Watson. And the definition of the standard error of regression in case of multiple regressors is very close to the one for a single regressor. So if you go back to last week, we have seen that the standard error of regression is defined as the square root of 1 over n minus 2 times the sum of the squared residuals if we have only one regressor, while here we have n minus k minus 1 rather than n minus 2. So if k is equal to 1 single regressor, then we get last week's formula as a special case. So this is a slight generalization. The only difference is that we have the k included down here. The interpretation is the same as in the simple linear regression model. And we can say that the standard error of regression gives us a measure of the typical magnitude of the error term. So it's not the average magnitude, and it's also not the average absolute magnitude. but it's in the range of a typical value. It gives an idea of a typical value of the error term. So this interpretation is exactly the same as in the simple linear regression model, and the definition of the formula in a way is also the same. It's only slightly more general, because here we can deal with k regressors rather than 1. The definition of R squared is absolutely the same as before. R squared is defined as the share of the explained sum of squares divided by total sum of squares, or which is absolutely equivalent, 1 minus the share of sum of squared residuals divided by total sum of squares. So that's really exactly the same as before. We can use this measure of goodness of fit as before. But there's a problem. If we use the R squared to say whether one model is better or another model is better in terms of goodness of fit, then we would always prefer models with more regressors. Why is that? Well, the reason is simple. If we add a new regressor to our model, then the R square will never decrease. It will in general increase, or in the worst case, it just stays constant. And the reason for that is that in the regression with more regressors, the case with fewer regressors is just a special case. So we can always get the same fit as with fewer regressors, but in general, we can even improve on the fit. So if we add regressors to our model, then R squared will never decrease, but in general will increase. So it's not a good idea to use R squared in this way as a device to say which model is better, because it would always prefer models with more coefficients in contrast to models with fewer coefficients, regressors. All right, and that's the reason why we introduce an adjusted R squared. The adjusted R squared has one additional term in front of the sum of squared residuals over total sum of squared. And this term here also includes the number of regressors. Okay. So this fraction here, the fraction in front of the term we are already used to, this fraction is always, is it larger or smaller? It's always larger than 1. Okay, so this fraction is larger than 1, and therefore we subtract more from 1 than before. And that's the reason why the adjusted R squared is always smaller than the unadjusted R squared. Usually not much, because n tends to be large and k tends to be small. And in that case, these two terms are almost the same, but in both cases, this fraction here is slightly larger than 1. The R square can increase or decrease if an additional regressor is included. Why is that? Well, if we increase the number of regressors, then k gets larger. If k gets larger, the denominator here gets smaller. Therefore, the fraction gets larger, which means that we subtract more from 1. And therefore, the R square tends to be smaller if we increase k. But on the other hand, if we increase the number of regressors, then the goodness of fit in terms of the sum of squared residuals will improve. And the sum of the squared residuals will get smaller. So this term here, the second fraction, gets smaller. So this fraction gets smaller, this fraction gets larger. And then it depends which of these two effects is stronger. And therefore, depending on whether the first effect is stronger or the second one is stronger, R squared, the adjusted R squared, can either increase or decrease when we add one regressor to our model. In fact, just as a little remark, R squared can actually be negative. That usually does not happen with economic data. Only in case of financial data that could happen. So if you encounter negative adjusted R squared, that's not a mistake. It can really happen. While the R squared, the unadjusted R squared, can never be negative. Okay, so let's have a look at the goodness of fit for the test score data set. If we only have a single exogenous variable, So this is the result from last week. We get an R-squared of roughly 5% and a standard error of regression of 18.6. The adjusted R-squared is very close to the unadjusted value. It's 4.9%. If we now add the percentage of English learners to our regression model, then the R-squared really jumps up dramatically from 5% to almost 43%. And also the adjusted R-squared gets much, much larger, from roughly 5% to 42%. And if we look at the standard error of regression, then the value goes down from 18.6 to 14.5, which is also a substantial decrease in the standard error of regression. So we can conclude that a single regressor, or the class size as a single regressor, can only explain a very small share of the variation in the test scores. So the class size is not responsible in this way, interpreted in this way, it's not responsible for the variation in the test scores. It can only explain very little variation. But if we add the percentage of English learners to our model and use both regressors as explanatory variables, then we can explain a much, much larger share of the variation, almost 40%, more than 40%. And also the standard error of regression falls considerably, so predictions are much more precise in that case. All right, so if we want to interpret the coefficients of our regression model, the beta 1, beta 2, and so on, the slope coefficients, in a causal way, which means interpret them in the way that Andreas has explained just before the active study break, namely as the change in the y variable if we adjust the x variable by 1 unit, keeping all other x variables constant. That's the causal interpretation of the coefficients. And this causal interpretation is only valid if a number of OLS assumptions is satisfied. We have already seen that in the single regressor model, and we repeat that and generalize that to the multiple regression model. So the first OLS assumption, which used to tell us that the expected error term is 0, no matter which value the regressor has, that condition is generalized now to the statement that the expected error term is 0, no matter which values all these regressors take on. Okay? So for all values of the regressors, the expected value of the error term must be 0. That's a very severe restriction, and actually that's the most severe restriction, and that's the one or assumption, that's the assumption that tends to be violated most often. And it's really a substantial assumption. It's not just a technical nicety. It's really inherently economic and really a substantial assumption, and we have to check that very carefully. The second assumption is almost the same as before. It tells us that the observations for all individuals or firms or whatever units we have are identically and independently distributed. That's really the same as before. The only difference is that we do not only have a single xi here, but we have x1i up to xki. Assumption number 3 is also the same. It used to say that the fourth moments of the regressor and the error term must be finite. It now tells us that the fourth moments of all regressors and the error term must be finite. I will say a few words to each of these assumptions in a minute. And then we have one more additional assumption here, which says that there's no perfect multicollinearity. That's new. And I will tell you briefly what that really means. But let's start discussing the first assumption. The OLS assumption number 1. So it tells us that the expected value of the error term is 0, given any values of the regressors. Now, what happens if there are omitted variables? So what happens if, say, another variable is relevant for the test result in the school example, California school data example, which is not included in the list of regressors? So the omitted variables are then just contained implicitly in the error term. And that means that the omitted variables, if they are correlated with any of the regressors, have an impact or have a relationship, a non-trivial relationship with the regressors, at least with one regressor, and they also have an impact on the error term. And in that case, assumption 1 would be violated. So if there is an omitted variable which is correlated with any regressor and has an impact on the error term, then assumption 1 would be violated. And then the causal interpretation is no longer valid. Because in that case, the estimators beta 1 up to beta k are biased. And the reason is exactly the same as we explained in the first part of this lecture. The reason is that this confounding effect really comes into play. The confounding factors which impact on the error term on the one hand side and on the regressors on the other hand. Okay, so in that case, we can say that to estimate the causal effects and to really have a valid causal interpretation of the coefficients, we must know that we have included all relevant regressors in the model. So even if a single regressor is missing, and if this single regressor is correlated with the other regressors and has an impact on the endogenous variable, a direct impact on the endogenous variable, then all coefficients are biased. And biased means that the value that we compute will systematically deviate from the true value. So it's systematically too large or systematically too small. And hence, what we think the causal effect is in effect wrong. Okay? So that's really a severe assumption, a very important assumption, and you should very carefully check this assumption in any empirical application. No matter whether you do this application yourself or whether you are just a recipient of somebody else's empirical investigation. Okay? So be very critical. Assumption 1 is really important. It's substantially important, not only technically important, and it can be violated, and it often might be violated. And then what you learn from the regression outcome is wrong. At least it cannot be interpreted in the causal way that we are interested in. All right. Second assumption. The second assumption just tells us that all observations are identically and independently distributed. And this assumption normally does hold if we work with cross-sectional data. So if the data are just randomly drawn with replacement, then that's not a problem. It's really a technical assumption if we work with cross-sectional data. On the other hand, if we work with time series data, we will do that in a special case with panel data at the end of the semester. But if we work with time series data, then it's not reasonable to assume that they are independent, because today's values often have an impact on tomorrow's values. So there's an intertemporal relationship between the variables, and then this assumption would be violated, which is why we start working with cross-sectional data, where this assumption usually should be satisfied. All right, assumption number 3. All the fourth moments are finite. That's also just a technical assumption, which always holds if the variables have finite support. For instance, the share of students which are English learners can only be between 0% and 100%. So it's a finite support, and variables with a finite support always have finite fourth moments. Also, if we can assume that the distribution is normal or Gaussian, then also the fourth moments are finite. So in general, this assumption is not really critical. It can be critical if you work with financial data, because financial data sometimes have really heavy outliers, and outliers might make the fourth moments infinite. So this is also another way to state this assumption. We do assume that there are no severe outliers in the data set. And the new assumption is assumption number 4, and it tells us that, that there's no perfect multicollinearity. Perfect multicollinearity means that one regressor is an exact linear combination of the other regressors. So linear combination, remember that. A linear combination is if you have a number of vectors, or in this case regressor values. A linear combination is a certain multiple of the first one plus a certain multiple of the second one plus a certain multiple of the third one, and so on. And if it's possible to find a linear combination of some regressors, which is exactly identical to another regressor, then we have the case of perfect multicollinearity. Okay, so perfect linear relationship between the regressors. And this must not happen, because in that case, it's no longer possible to really compute. Let me go back. To really compute, sorry, to really compute the values b1 up to bk, which minimize our objective function here. So the LLS estimators just cannot be computed for technical reasons, because the minimization approach involves a linear system of equations. And this equation system cannot be solved if we have multiple, if we have multicollinearity. So in that case, it's technically impossible to compute the estimators. Can that happen? Could it really happen that we have a case of perfect multicollinearity? And the answer is not really. It could happen, but in that case, usually what you did is you made a mistake when you collected the data. A very trivial example is, by mistake, the same regressor appears twice in your model. For instance, you compute the percentage of English learners and you call it PCTEL. And then you have a second variable, which is called share of English learners, say SHEL, but they are completely identical. In that case, of course, one regressor is an exact linear combination of the other regressor. It's just the same regressor. And in that case, it would not be possible, obviously, to distinguish the effect on the endogenous variable of these two variables. So in that case, to rectify the problem, to solve the problem is very easy. Just drop one of these two variables, because it's already there in the other regressor. The second trivial example, you introduce two dummy variables which in a way measure the same thing, or which incorporate the same information. For instance, you can define a dummy variable di, as we did last week, which is 1 if the class size is small and 0 if it's not small. And then you could define a second dummy variable, which is 1 if the class size is large and 0 in the other cases. Then if you sum up these two dummy variables, you get a vector which is just a vector of 1s. And the vector of 1 is already included in the model as the intercept. So in that case, these two dummies together give the same information as the intercept. And therefore, again, we have the case of perfect multicollinearity. So in short, perfect multicollinearity is a problem that could happen. And you would realize that because you get an error message from your computer package. It will tell you that it cannot compute the estimators. And therefore, you should go back to your data collection procedure, because very likely you made a mistake when you set up the data set. Either a certain regressor appeared more than once, or you included the same information in different ways. Okay, so I hand back to Andreas now.
Thanks, Mark. I have to say now, I have to be a wise guy here. R is very user-friendly here, so R doesn't drop you an error. It tells you that it couldn't compute anything, but it actually drops one of the problematic variables automatically and then computes your OLS regression and drops a warning regarding that you had perfect multicollinearity, but everything will be computed in order already with a warning that one of the variables had been dropped. Now, to finish today's session, there's a little more to say, namely on the distribution of our estimators, something we have encountered 2 weeks ago as well, and where we have seen that the estimators are random variables, and we can use that knowledge that the estimators are random variables later on to test them, to test whether or not, for example, they are significantly different from 0. And to do that, we need a distribution of our estimators. And as we've seen 2 weeks ago, the exact distribution of the OLS estimators under our assumptions is complex, too complex to discuss it here. But fortunately, we very often have large data sets, and that leaves us or allows us to use the asymptotic distribution. And that one is very simple because our estimator, beta1 hat, is asymptotically distributed normal with an expectation of the true value and some variance. We can derive formulas for that variance at sigma squared of beta1 hat, and we might do the same thing for all our regressors. Luckily, we don't need to do that ourselves, but R or any other statistical programming language or software does that for us, so that we don't need to focus on deriving the formulas for this estimate or deriving and estimating this variance, but we can directly jump into the standard error of beta1. So the standard deviation of our error term is just the square root of sigma squared hat of beta1 hat. So here the square root of the estimator of the variance of our estimator of beta1. And then we can see that approximately it holds, at least in large samples, that beta1 hat, our estimator, minus beta1, the true value, divided by the standard deviation of beta hat, is normally distributed, and it is standard normally distributed. So we can, and we will see that in the next week, derive the whole set of t-tests that we derived for the simple linear regression model, also for the multiple linear regression model. So all the things we did back a week ago still hold in our multiple linear regression model. So that's what I wanted to say today. I think we finished a little earlier today. So thanks for being here. I hope you enjoyed the active break again. Let us know in the exercises again, and then see you on next Monday.
Unless there are any questions, of course.
Unless there are any questions, as usual.
And we might stop the recording soon.